Welcome to this seminar with Noah Fleming from the University of Toronto. Noah has, over the last few years, done some groundbreaking work on different semi-algebraic proof systems that notably cutting planes and stabbing planes that capture, for instance, some of what mixed integer linear programming solvers can do. And Noah will tell us about some of the latest news today. Please.
Yeah, thanks so much for having me, Jakob. And thanks for the lovely introduction. Yeah, so I'm going to be talking about our really recent paper on the power and limitations of branch and cut. So this sounds like an integer programming talk. It's actually a proof complexity talk in disguise. So sorry about that. This is joint work with kind of the regular suspects. So we got Goose, Liang Tan, Ruslan Pagliazzo, Tony Patassi, Robert Robert, and Avi Vigderson. And kind of the outline of the talk is going to be as follows. We're going to talk about how we can use proof complexity in order to analyze practical algorithms. And then we're going to look at this in the context of integer programming. And we'll talk about cutting planes and also kind of what is done in practice right now in integer programming, this branch and cut. And how this relates to another proof system called stabbing planes. Then we're going to compare stabbing planes and cutting planes and show how they relate to each other, sort of. And then we'll show how to use these relations in order to get short proofs of systems of linear equations over finite fields in cutting planes. And at the very end, I'll go into some detail on some depth lower bounds on cutting planes and how they relate to a conjecture that we have. Okay, so algorithms from proofs. So you're probably sort of familiar with this. Basically, proof complexity provides like a nice way to analyze practical algorithms. So what you can do is you can formalize the techniques used in a class of algorithms as a proof system. This sort of hides the practical details of the algorithms, and then lower bounds on the length of proofs in these proof systems imply lower bounds on the runtime of the algorithm. Okay, so standard examples are the CDCL SAT solvers. So these can all be formalized by the resolution proof system. Then there's algorithms for integer programming. So the classical Chvátal-Gomory cutting planes algorithm corresponds to the cutting planes proof system. There's also lots more examples here, like the sort of duality between Shirali atoms and this like broad family of linear programs, and same for sum of squares in the Lasserre hierarchy. But yes, we're going to be focusing on integer programming in this talk. So what's integer programming? So you're given a system of integer linear inequalities, and you're asked to find an integer solution to them. So of course, this is NP hard. And because we have linear inequalities, we can view this geometrically. So we're given a polytope, and we're asked to find an integer point in it. And I should warn you guys that, so this is going to be sort of like my IAS talk, or I mean, my Simon's talk, except for I'm going to go into detail on all the proofs, basically. So I'll give you all the good stuff. Okay, so yeah, a classic approach for solving integer programming problems is Chvátal-Gomory cutting planes. So it's like a class of algorithms or a method. In order to define what that is, we need the notion of a CG cut. So here we have a valid half space. That means that like every point, like every rational point in the polytope or real point in the polytope satisfies that linear inequality. And from it, and we're going to assume that A is integral, but B can be rational or real. And a CG cut is obtained from this valid half space by just rounding it. So we take the ceiling of the right-hand side and pushes the half space in. And so this rules out some fractional solutions, but maintains integer solutions. Okay, and yeah. So Chvátal-Gomory cutting planes is just a method to heuristically add CG cuts to a polytope P until either...
Noah, the way we should think about your picture now, sorry, I guess I haven't had enough coffee, but we should think that the red corners with crosses, those are the integer points.
Yeah.
And
yeah,
all these
yeah.
grad stuff inside, green stuff inside is like the rational stuff, and that was why you could cut all the way until you touched the topmost
Yeah,
right.
very, very good. Yeah. Yeah.
Okay, perfect. Thanks.
Yeah, so the little x's are going to be integer points throughout. And yeah, so you can remove some fractional stuff, but you're never going to remove any integer points using this rule.
Perfect, thanks.
Yeah, so that's what CG cuts, or I mean, Chvátal Gomory cutting planes does. You basically just add CG cuts to the polytope until either an integer solution is found or the empty polytope is deduced. And so this can be like easily interpreted as a proof system, and this was observed by Collard-Turan in the 80s. So in this case, so we're going to focus on polytopes with no integer solutions, and we want to prove the fact that they have no integer solutions. Okay, and so a cutting plane's proof of this fact is just a sequence of polytopes, where the first polytope is the initial polytope, and each subsequent polytope is deduced by adding in an additional CG cut. So here we have P1, the initial polytope. There's a valid half space, there's a CG cut, another valid half space, CG cut, P3, valid half space, CG cut, you get P4, and again, you get P5, P5's empty. So this is a cutting plane's proof of the fact that this polytope didn't have any integer solutions. And the size of the proof is just the number of polytopes in this sequence. Yeah, and so in proof complexity, cutting planes has been extensively studied. It's quite powerful, so it has short proofs of the pigeonhole principle, but not so powerful that we can't prove lower bounds on it. So in 97, Pudlock obtained the first exponential lower bounds on cutting planes proofs. And on the right here, I have this little picture of the proof system hierarchy, or a hierarchy of like pretty standard proof systems. So the ones in green are those for which we can prove exponential lower bounds. And the ones in yellow are ones where we can't yet prove strong lower bounds. Yeah, so although cutting planes is quite well studied in, and it's been really impactful in proof complexity, in practical integer programming, cutting planes usually isn't just used by itself. It's kind of used as a subroutine. So what modern integer programming algorithms do is they combine cutting planes with a branch and bound procedure into what is known as branch and cut. So here again, we have a polytope, and this time it has some integer points in it, so these red X's. And we're going to repeat the following two procedures. So first we branch. So we break the polytope P up into subpolytopes, P1 to Pk, such that every integer point is contained in one of these polytopes. So here's one way of branching. You get two polytopes there. You can observe that all the red X's are contained in one of the polytopes. So in practice, this branching is done, well, it can all be seen as like, all the branching in practice can be seen as a like a subset of the following general rule, where you pick an arbitrary half space, integer linear half space, and branch on whether it's greater than or equal to, you pick some ax greater than b and branch on whether it's true or whether its integer negation is true. So that is ax is greater than or equal to b, or ax is less than or equal to b minus 1. And so in practice, usually what is done is like branching on the value of a variable. So we can ask like, is this variable greater than or equal to 1, greater than or equal to 2, greater than or equal to 3, that sort of branching, or branching on the value of a Hamming weight of a subset of coordinates. And then there's also like sort of basis reduction things in the style of Leenstra's algorithm. But yeah, the point is they can all be captured by this general rule here. And then the second thing you do is you cut. So this is where cutting planes comes in. You refine each of these subpolytopes by adding additional cutting planes. Like that. Okay. So of course, cutting planes is only a subroutine of these algorithms. So it doesn't, like lower bounds on cutting planes don't imply lower bounds on these modern integer programming algorithms. Yeah, and we repeat this process here. So in 2018, we introduced the stabbing planes proof system, which formalizes practical algorithms for branch and cut. So stabbing planes is quite simple. In fact, it can be seen as like an extension of the standard DPLL algorithm to reason about linear inequalities. Okay, so I'll remind you what DPLL is.
I'm actually a bit curious here. It's sort of a little bit beside the point, but I'm just curious, where did this come from? I'm like, you're stabbing planes, the realization that, and also like, is it then correct that you found nothing? Like, I mean, the MIP solvers are fairly old by now, but no attempts from like the MIP side to analyze in terms of proof systems, or like stabbing planes is, for all we know, like the first proof system.
Yeah. So, where did stabbing planes come from is a good question. I was working with Antonina during my undergrad, and we talked about various proof systems that we could analyze. We ended up like talking with Russell, and we settled on this stabbing planes proof system. And we realized that it could be useful for practical SAT solving, like some sort of pseudo-Boolean solving. And I think we were also aware that it was related to like branch and cut at the time. Although, yeah, I think at the time we basically thought most of what branch and cut was doing is branching on variables. And as for your question as to whether this has really been analyzed as a proof system before, like branch and cut has, I don't think so. So I've been writing my thesis and I did a pretty deep literature dive, and I haven't seen anything that would have, So what people have done in integer programming literature is they have analyzed like branch and bound as a proof system, which is basically DPLL. And there has been, I think, one paper which proved lower bounds on branch and bound, where you're able to branch on, branch and cut, where you're able to do cutting planes deductions plus like branching on single variables. But like a general framework where you're able to branch on linear inequalities, to my knowledge, hasn't been studied before.
Also, in terms of modeling power, I wonder if you were underselling it a little bit, in the sense that, of course, modern MIP solvers, they have all kinds of, they're pre-processing. We don't know what they do, the commercial solvers, and they have some special purpose dynamic programming algorithms and all kinds of magic. But apart from that, like the basic branch and cut, any LP solving that is happening in between, cutting planes has no problem in modeling that, right? So like, in some sense, it's a similar situation to CDCL. It seems to me that modulo pre-processing, like resolution is it for CDCL, right? And here modulo, like the fancy tricks that could be whatever. Stabbing planes is strong enough to take care of pretty much anything that goes into the basic MIP setup.
Yeah. And I'll get into this, I'll mention it a little bit later, but stabbing planes also doesn't just capture like cutting planes cuts. It can capture basically every other type of cut that is done in practice.
Okay.
And this was, I think, recently observed by Amit Basu and some other people as well. But yeah, I think you're basically right that up to pre-processing, it basically captures what you can do, unless you were to branch on some object, like do the branching step for something that isn't linear, but then you might not get polytopes. So you'd have to be careful there. Yeah. Okay. So we'll get to that in a minute. So DPLL, you all probably know this. You start with a CNF formula, and you basically build a decision tree refutation of it. So you pick a variable, you query it. You ask whether it's 0 or 1. Now let's go down to left branch. You pick another variable, you ask whether it's 0 or 1. We're just searching for a satisfying assignment. On the leftmost branch, we falsify this clause, and so we recurse, and we keep doing this. And at every leaf, we find a falsified clause, and so this is just a proof of the fact that the initial CNF formula is unsatisfiable. Okay, so we're interested in integer programming problems. So let's rephrase DPLL in the world of integer programs. So here I have translated the CNF formula that we had before into a system of linear inequalities. It's satisfiable over the same set of integer points as the CNF was. And one thing to note is that we have these constraints on the rightmost side, which say that every variable falls in the Boolean cube. So then we can, of course, we can view this as a polytope, and the root node of the DPLL tree is going to be associated with just the full polytope. Now we branch on a variable, and we're going to query whether x1 is less than or equal to 0 or greater than or equal to 1. And why is this the same as before? Well, because we have these constraints saying that the variables fall in the Boolean cube. This is the same as asking whether x1 is 0 or x1 is 1. And here you can see the red lines are kind of the action of this branch on the polytope. So if we go down to the left branch, and this corresponds to restricting to this polytope where we have P intersect with the inequality x1 is less than or equal to 0. And now we just have this tiny little dot on the corner of the polytope, and we can branch on x2, and this removes it, and we derive the empty polytope. So there's no points in this polytope, so clearly no integer points. And observe that this branching rule, where we're branching on whether x1 is less than or equal to 0 or greater than or equal to 1, this preserves any integer points. If you had an integer point, it would satisfy one of these two. So it's only ruling out fractional points. You keep doing this, you derive the empty polytope at every leaf, and this is a proof of the fact that the CNF is unsatisfiable. So what's stabbing planes? Well, it's just the straightforward generalization of DPLL to branch on linear inequalities instead of single variables. So you start with the polytope, you pick an arbitrary integer linear inequality, and you ask whether it's true or its integer negation is true. And here you can see kind of the action of it on the polytope. So the arrows point to the two sides of the query, and there's a slab down the middle that is being removed from the polytope. And because A and B are integral, this cannot remove any integer points. It only removes some rational points. Yeah, and so let's go down the left branch. We restrict to this polytope, and we keep going, keep querying until we derive the empty polytope at the leaves. And now we go down the right branch. Again, we're at this polytope, and we derive the empty polytope. And so because at every step we're only removing fractional points and we preserve integer points, if we can derive the empty polytope at every leaf, then this is a proof of the fact that the initial polytope contained no integer solutions. Yeah. And the size of a stabbing planes proof is just the number of queries in it. And this was recently shown to be polynomial equivalent in a really nice work by Dadush and Tiwari. So polynomial equivalent to the bit complexity of actually writing down this proof. Yeah, okay. So natural question is, we have two programs for, proof systems for integer programming. How do they compare? So I said that stabbing planes formalizes branch and cut. So branch and cut was allowed to use cutting planes deductions as well as this branching. So we have to show that stabbing planes can simulate cutting planes, and this is true. And in fact, we characterize stabbing planes as like a non-trivial cutting planes as a non-trivial subsystem of stabbing planes, which we call path-like stabbing planes. This is pretty obvious. So what is path-like stabbing planes? So a path-like query is, so we're going to call this branch like ax greater than b, ax less than or equal to b minus 1, a query. So a query is path-like if one half of the query is the empty polytope. So for example, this is not path-like. You're stabbing through the middle of the polytope. Whereas this one is, because the left branch is empty. Okay, and why is it called path-like? Well, it's one big long path. So in order to show that path-like stabbing planes is equal to cutting planes, you have to show that every CG cut is a path-like query. So here's a CG cut. There's the valid half space, say x greater than or equal to b, and you round it. Okay, and so if ax greater than or equal to b is valid, then this means that ax less than or equal to the ceiling of b minus 1 is going to be the empty polytope, and this shows that the query where you take ax less than or equal to the ceiling of b minus 1, ax greater than or equal to the ceiling of b, is a path-like query, and that shows that they're equivalent. Yeah. So then a natural question from this is whether we can separate the power of cutting planes from stabbing planes. Can we show that stabbing planes is actually stronger than cutting planes? So a natural candidate was the Tseitin formulas, and maybe you've already had this spoiled for you if you saw Dadush and Tiwari's talk a few weeks ago. So there's quasi-polynomial size stabbing planes proofs of the Tseitin formula. So we showed this in the 2018 paper, and they were conjectured to be hard for cutting planes for ages. This was even in the initial paper that proposed the cutting planes proof system. So Dadush and Tiwari showed in a really surprising work that there are quasi-polynomial size cutting planes proofs of Tseitin. How did they do this? Well, they showed that these stabbing planes proofs of Tseitin could be translated into cutting planes. This was really surprising to me. So this raises a natural question, can every stabbing planes proof be translated into cutting planes? Is stabbing planes just equal to cutting planes? This would be really nice because this would, then we could view stabbing planes as kind of like a query-based model for cutting planes, like how DPLL is a query-based model for the rule-based proof system tree-like resolution. Okay, so we give a partial answer to this. We show that every stabbing plane star proof, so this is stabbing planes where the coefficients have a quasi-polynomially bounded magnitude, can be quasi-polynomially translated into cutting planes. And this means that we can sort of use stabbing plane star as a query proof system for cutting planes. Up to large coefficients on both sides. So how do we prove this? So first we showed that cutting planes is equal to this path-like stabbing planes. Now we're going to show that it's equal to something that seems stronger, called face-like stabbing planes. So remember that this was path-like stabbing planes. One half of the query had to be empty. So face-like stabbing planes relaxes that and says, okay, you don't need one half of the query to be empty. One half can be a face. That is, ax less than b minus 1 has to be empty, but ax equal to b minus 1 could be non-empty. That means that ax less than or equal to b minus, or ax equal to b minus 1 is like a face of the polytope. Okay. And then second, we show that any stabbing plane star proof can be made face-like with a quasi-polynomial blow up in the size. Yeah. Okay. So how do you show that cutting planes is equal to this face-like stabbing planes proof? So here's a face-like query on the right-hand side, and I'll just show you how to do it on this example. So the simple observation is that if we could refute the polytope P intersect with ax equal to b minus 1, or the face here, then we can deduce that the polytope P intersect with ax greater than or equal to b. That is, we can deduce the right-hand side of this query in path-like stabbing planes. That's just because ax less than or equal to b minus 1, ax greater than or equal to b would be a valid path-like query if we had proved that the face here is empty. Okay, so here's an example of some proof. Right, so we query ax greater than or equal to b, and then on the left node, we query cx greater than or equal to d. And we're going to say that here f is going to be the face of the polytope, right? and yeah, please interrupt me and ask any questions if something is not clear. So this, I've just drawn a face-like stabbing planes proof, some arbitrary one. We're looking at this face here, and at this face, the face-like stabbing planes proof has two children, both of them labeled with the empty polytope. So there's a picture of the final query on the face. So we derive the empty polytope, and observe that if we look only at this face, F, then this query, Cx less than or equal to D minus 1, Cx greater than or equal to D, is a valid path-like query for F. And this is just because, both sides of F are, after applying this query, are empty. So this means that if we, so at the leaves, we have path-like queries. And what we'd want to do is sort of like lift these path-like queries up to the polytope P. So how we should be thinking is so we have a refutation of F that is actually path-like. Can we lift this up to P? Can we take this refutation of F and turn it into something that acts on P, such that we can derive a polytope P prime from it, such that P prime intersect with the face is empty? That means, like, this is saying, can you use this refutation of the face in order to refute the face still when starting with the polytope P? And that's kind of the general high-level idea of what we want to be doing here. So we're going to say that a polytope P derives a polytope P prime if P can be obtained by a single path-like query, or that P prime can be obtained by a single path-like query from P. So that means P prime is obtained by a single CG cut from P, since CG cuts and path-like queries are the same. And the main key that lets us lift path-like refutations of a face up to refutations of a face on the higher polytope is this Shriver's lemma. And it, I asked that question back here. This thing, can we simulate a refutation of F when starting from P? Shriver's lemma basically just says, yes, you can do that. And this was also the main key lemma in Dadush and Tiwari's simulation of, Dadush and Tiwari's, cutting planes proof of the Tseitin formulas. Okay, so what does it say? It says that if you have a face F of some polytope, and from this face, you can derive a new polytope F prime. Then there's a polytope P prime that can be derived from P, such that if you look at P prime, if you take P prime and you look only at the face F, then this is contained within F prime. So basically, P prime is at least as strong as F prime.
Question.
Yeah.
And I don't know if I'm headed in the wrong direction or if I'm getting ahead of things, but you had this blue and were they blue and green, the queries on your previous slide?
Let's see. Yeah, these guys here.
Yeah. So is the idea somehow that I could somehow take the blue inequality and multiply it by something really big and then pack it into one joint inequality with the green guy?
Oh, maybe.
Suppose I take a really, really large number, sufficiently large, some k, right? And I multiply the blue inequality by k, and I just sum it up with the green guy, and then that joint inequality will be true only if. No, that won't work. No, that will work only for an equality.
You're kind of on the right track, actually. You're asking for the proof of the
Yeah.
So I'll go through that in a very quick sketch, but that sounds pretty close to what you do.
Okay.
So a very quick sketch. Here's a polytope, and we are looking at the face A, which is the polytope intersect with AX equal to B. This is just the general idea of the proof. I'm not going to be too formal with it. And let's say we can derive F prime from F by the CG cut CX greater equal to the ceiling of D. Right? So the observation is that, okay, we're going to say that AX greater than or equal to B is valid for the polytope P. And the only thing we don't have, the only thing that is valid for the face, but is not valid for the polytope P is AX less than or equal to B. Okay, so what we want to do is we want to take CX greater than or equal to D, this guy, and shift it so that it doesn't depend on the inequality that is not valid for P. It doesn't depend on AX less than or equal to B. And if you can do that, and the cut you have is still just as strong, then this will be the thing you want. Yeah, so you want to take CX greater than D, shift it to C prime X greater than D prime by taking some large, by like basically adding AX greater than to B enough times so that it no longer depends on AX less than or equal to B. And yeah, and so that means that you can deduce C prime X greater than D prime from the polytope P, and you get the final thing you want, that P intersect the round of C prime X greater than D prime is intersect with F is then contained in F prime. And the thing that I haven't said here, which is pretty crucial to it, is that if we're looking at this face, if we're looking at AX, when we've restricted to AX equal to B, like every point on this face satisfies AX equal to B. So if we add factors of like integer if we add like integer multiples of AX greater than to B, then this doesn't affect anything on this face. Like it doesn't affect any of the points on the face because all of the points on the face just satisfy AX equal to B. And that's kind of the high level idea of what is going on in.
But that's really why you need to be on the face, right? Because so that's somehow the magic that,
exactly.
Just adding AX on one side and B on the other, but they happen to agree. So it's like nothing happens on that particular face. Everywhere else in the polytope, it would be catastrophe, but here it somehow works.
Yeah, exactly. And yeah, so then you just get a cut that's just at least as strong, and that's basically the proof of the Shriver lemma. Okay, and then the proof that cutting planes is equal to face-like stabbing planes is just basically straightforward from the Shriver lemma. Like all you do is you take an in-order traversal of the stabbing plane's proof using this Shriver lemma in order to simulate each of the lower queries by higher queries, and you just kind of lift them up. So here's our example from before. There's our face, and we want to take the query, right, so we had this valid path-like query CX greater than D from the face. So the face we derived is F prime, and we're going to apply the Shriver lemma to it. So by the Shriver lemma, there's a polytope P prime such that it can be derived from P, and such that P prime intersected with the face. If you look at P prime on this face, then this is contained within F prime, but F prime is the empty polytope, and so this refutes the this shows that P prime intersect with F is the empty polytope. And because of this, there has to be some epsilon greater than or equal to 0, such that AX minus B plus epsilon, AX greater than or equal to B minus 1 plus epsilon is valid for P. And all I'm saying here is that from P, the face-like query, AX less than or equal to B minus, path-like query, AX less than or equal to B minus 1, and AX greater than or equal to B is valid for P prime. And this allows us to deduce the polytope P intersect AX greater than or equal to B. So what we've done is we've used the Shriver lemma in order to simulate this refutation on the face when we just started with the polytope P. Okay, and this is the whole proof that cutting planes is equal to this face-like stabbing planes thing. And now we want to show that we can quasi-polynomially simulate static plane star. So here's the formal statement of the theorem. So any static plane's proof of size S and coefficient size C, so this is the magnitude of the coefficients, or the maximum magnitude of them, results in a size S times C times N to the log S, a size face-like static planes proof, or cutting planes proof.
Do you know if this is tight?
No, no, I'd be really interested in knowing that. I think if you were to show that it's tight, well, you might be showing a lower bound for cutting planes on the Tseitin formulas, which would be also very cool, like a quasi-polynomial lower bound.
Oh,
Oh, maybe not actually.
it's not a priori obvious because you have like a particular way to simulate stabbing planes, and there might be other crazy ways that we know nothing about, right?
Yeah, I would be really interested in knowing if this is tight. Like, it seems like maybe you could do some sort of tricks or something in order to improve this simulation, because this simulation is like pretty dumb. Like, you just kind of do the obvious thing, maybe obvious after you've thought about it for a few years, but yeah, I'll show you. It's very simple, and yeah, I'd be really interested if somebody could improve this. I feel like maybe you could. Yeah, okay, so I'm going to show this for polytopes in the Boolean cube, but this holds for others. Basically, it holds for polytopes outside of the Boolean cube. You get a dependence on the diameter of the polytope, like the distance between the longest distance between any 2 points in the polytope. So there's some decay with that. Yeah, so to prove this, let's fix a stabbing plane star proof pi. Here's a little drawing of the proof. So we start with the polytope P, and then on the left branch we carry AX less than or equal to B minus 1, and we have a subproof pi L. And same, we have a subproof pi R on the right-hand side. So this is what it looks like on the polytope, right? So the green space is P, and then here's the query. And we're going to suppose that the left-hand side of the proof pi L is the smaller side. Okay, and so now let's let B0 be the largest integer such that AX greater than or equal to B0 is valid for the polytope P. So that means like every point in the polytope P satisfies it. So what we're going to do is we're just going to start at AX greater than or equal to B0, and we're going to layer it with queries from the left all the way up to AX greater than or equal to B. So this is what it looks like down here. Yeah, I told you it was the dumbest thing. So then you can observe that this little proof here, where we started at AX greater than or equal to B0 and went up to AX greater than or equal to B, this is a face-like proof. Because, you know, at the polytope where you have AX greater than or equal to B0, then AX, when we query, sorry, that should be greater than or equal to B0 plus 1 on the second query. But you can observe that AX, after the query AX greater than or equal to B0, then AX equal to B is a face of the resulting polytope. And so this is a face-like proof. So now we just need to patch up this proof. Like, now we need to refute each of these little branches here. Okay, so how can we do this? Well, observe that pi L refutes everything in the left-hand side of the static planes proof. So it refutes all of that. So we can just use this. So we're going to let pi L prime be the refutation pi L obtained by recursively converting it to a face-like proof by just doing the process we're doing now. And then we're just going to, patch pi L prime onto each of these leaves here. And then we're going to patch pi R prime onto the rightmost guy. And that's the proof basically. So there's a dependence on coefficient size. Well, why is this? So the slab, like the area that is ruled out between two queries, the width of this slab is dependent on the magnitude of A. In fact, it's 1 over the 2 norm of A. So what does this mean? If the magnitude of A is not too large, then each of these slabs is quite large, and the distance between B minus B0, the number of cuts that we have to do like this, is not too many. And yeah, that's basically the proof. So any questions? Okay. So we showed that every stabbing plane star proof can be quasi-polynomially translated into cutting planes. I'm not going to do the numbers, but you guys can work it out. So some corollaries from this, we get an exponential, or well, at least 2 to the n to the epsilon lower bound on stabbing plane star. For the following formulas, we get clique, co-clique, random CNF formulas, and lifted formulas. There's the corollary that stabbing plane star cannot be automated unless P equal NP. And this is just by inspection. And then the last one is something which is kind of cool, that cutting planes has quasi-polynomial size refutations of any unsatisfiable system of linear equations over a finite field. And this is a little striking because on the other hand, there are unsatisfiable systems of linear equations, not on a finite field, which require exponential size cutting planes proofs. And this was shown by Chvátal and others. So this presents an interesting dichotomy. Like you can reason about equations of finite fields, but maybe not equations in general. So how do you do this? This one's pretty simple. So first, we're going to show a general algorithm for refuting systems of linear equations over finite fields, and then we're going to show how to implement it in stabbing planes. And I'll show it for systems of F2 linear equations. This is slightly different than our refutation of the Tseitin formulas in the earlier 2018 paper. And it kind of has most of the ideas, but avoids some annoying case analysis. So here's a system of linear equations over, and we're going to assume they're all over like F2. So we can view them as hyperedges. Graph, it's just a nice picture. And I'm going to let E be this set of all these edges, or so we're going to first partition. So it's going to be a divide and conquer algorithm. We're going to partition E into 2 sets, E1 and E2, which have approximately the same size. So there you go. And then we're going to let this cut, this 2 cut, be the, so it's going to be, so you're going to take in a subset of these edges, and the 2 cut is going to, you're going to basically sum up all of the variables in the edges mod 2. So the 2 cut of E1 is the same as 2 cut of E2, which is X4, X5, and X7. It's the variables that occur an odd number of times in each of these equations. Okay, and then we're going to branch on the parity of the sum of the 2 cut. Okay, so let's suppose that the parity turned out to be even. Well, because the system's unsatisfiable, this means that one of the 2 halves has to be unsatisfiable under this assignment to the parity, and so we can throw out half the equations. So in this case, E1 is unsatisfiable, and we can recurse on E1. So again, we're going to partition the remaining edges into 2 halves. we're going to query their two cut. So these are the two cuts. Now they're not equal. But again, we're going to branch on the parity of each of them. So let's suppose that we found out that they're both odd. You can't simultaneously satisfy both of them, or you would have violated the previous round. And yeah, so under this assignment, E1 is unsatisfiable and you recurse on it. You're down to two equations, you partition them, you branch on their cut, and one's going to be falsified, and you found a falsified constraint. Okay, so this is the simple algorithm. And now we just need to show how to implement it in stabbing planes. And again, yeah, you do the dumb thing. So you want to determine the parity of this two cut in stabbing planes, but stabbing planes can't branch on mod 2, like it can't branch on parities. So what do? You just branch on what the value of this two cut is, overall possible values it could take. So that's all it's doing here. You're asking, like, is the value of this cut 0? Is it 1? Is it 2? Is it all the way up to its maximum value? And this gives you a big long proof like this. And on each of the leaves, you've determined exactly the value of this two cut. And so then you can recurse on, you can recurse on the algorithm. Okay, and once the parity has been determined, you can recurse on the unsatisfiable side. So what's the complexity of this? Well, we have log n recursive rounds because we're throwing out half the equations every time. And the value of each two cut can be between, basically between 0 and n squared. And this gives you an n to the order log n size stabbing planes proof. And you can, so to do this for systems of linear equations over some other finite field, you basically do the same thing. There's some little tricks. Basically, if you have an unsatisfiable system of linear equations over a finite field, in this case, there's going to be like a non-negative linear combination of the equations, which equal to 0 equal 1, and then you kind of branch on this non-negative linear combination in order to find a falsified constraint, but it's pretty simple. Okay. Yeah, so the last thing that I wanted to talk about is this really weird observation. So in both our proof of the proof that we get of these mod 2 linear equations and the proof that Dadush and Tiwari get of the Tseitin formulas, in both of them, so they're quasi-polynomial size, but they also have quasi-polynomial depth. So these proofs are extremely deep. And this is mostly a consequence of applying this Shriver lemma over and over again. So this brings up a natural, so any CNF formula can be refuted in depth n in cutting planes. And so this brings up a conjecture that we had, which is that any quasi-polynomial size cutting planes proof of the Tseitin formulas requires super linear depth. So depth that's above worst case. So this is, we're conjecturing that the Tseitin formulas are an example of like a supercritical trade-off between size and depth for cutting planes. Yeah, okay. And so the last part of the paper, we make some, well, we think it's progress towards this. It's hard exactly to say, but I think the result's interesting on its own. So one of the problems is that we just need a better understanding of cutting planes depth in order to resolve this conjecture. And we provide a new method for proving lower bounds on cutting planes depth. Our technique is kind of geometric, and it also works for semantic cutting planes. So we get the first lower bound on the Tseitin formulas for semantic cutting planes.
And what do we mean by semantic cutting planes? We mean the rule is still binary, but anything I can derive from anything implied by two linear inequalities, I can have it.
Yeah. So in syntactic cutting planes, you had the CG cut rule. In semantic cutting planes, you're just allowed any sound inference, but fan-in has to be 2. So semantic cutting planes only works for polytopes in this should be 0, 1 to the n. So we're going to only look at those. And our goal is to derive the trivial unsatisfiable linear inequality 0 greater than equal to 1. And we have all of our axioms A1, X greater than B1. They're all the inequalities in AX greater than equal to B.
And I guess I should know this, but the semantic cutting planes, we know that this is exponentially stronger than syntactic because you can somehow pack, I guess, knapsack type problems in this framework. They will be easy to solve. Or
exactly.
I think we have some people in the audience who probably did this. I'm, embarrassed that what Filmus, Lauria, someone else.
Yeah. So I think they all showed that. Or you can go ahead, Yuval. I saw you unmute.
Right. So the point is that subset sum is easy to refute in semantic cutting planes. So kind of the idea is to take a bunch of equalities and to put them together as one inequality, which is something you can do, and then refute it in one go in semantic cutting planes. This is something you can't do in syntactic cutting planes sometimes.
Yeah, it's really cute. And you also showed that you could like reformulate clique, co-clique to use equations rather than inequalities. And then you could separate semantic cutting planes from cutting planes, like using a regular CNF formula, right?
Right. So you can encode, let's say, a constant width clause as an inequality by adding some dummy variables. So this way, everything becomes an equality with these extra variables that we don't care about, and we can just pack them into a single equality, which we can refute in one step in semantic cutting planes.
Yeah, that's a super nice paper.
And just to mention, so Massimo mentions in the chat, this is Yuval, Filmus, Massimo, Lauria, and Pavel Hrubesh, just for the record. Yes. Okay, great. Thanks.
Yeah, so as Yuval was saying, like the cool thing about semantic cutting planes, we can prove lower bounds on them, but it's not even like polynomially verifiable. Like this knapsack problem shows that you can't even polynomially verify these proofs. They're extremely powerful in some dimension. So in semantic cutting planes, you're allowed the semantic deduction rule. You can take 2 inequalities, you can derive a new one, so long as the new one is satisfied by every Boolean assignment which satisfied the 2 ones that it was derived from. And the depth of the proof is just the length of the longest root to leaf path in the DAG here. And similarly, so I haven't defined cutting planes depth yet, but the depth of cutting planes, you can just replace this DAG with deductions, which we're using the CG cut rule instead of the semantic deduction rule, and then the depth becomes the depth of the DAG. And depth kind of captures like the parallelizability of these proofs, and therefore like algorithms which are captured by these proof systems. So it's a pretty natural parameter from that perspective. So previous lower bounds on cutting planes were proved by either reduction to the Chvátal rank or communication complexity. And so if we wanted to prove a size depth trade-off, like a supercritical one, both of these present some problems. So on one hand, like communication complexity, there are linear upper bounds. If you want to prove it for Tseitin, there's like order log n depth communication protocols for the Tseitin formula. So these communication complexity cannot be used to refute, or I mean to prove or refute this conjecture. And there's also problems with the Chvátal rank, as I will mention. Yeah, so order log n, upper bounds, and Tseitin in communication. And so what's the Chvátal closure? So this is, yeah, so the Chvátal rank is defined in terms of Chvátal closure. So you take a polytope P and you derive P superscript 1 by adding all possible CG cuts that are valid for P to P. So here's a little picture. There's all the possible valid half spaces, and there's their rounds of them. And so we're going to similarly let PI be the polytope obtained by taking I rounds of this Chvátal closure. And then the Chvátal rank is just the minimum T such that the T round closure of the polytope is empty. So if we want to show, so for a depth bound of D, we want to show that the polytope obtained by taking D rounds of this closure procedure is non-empty. That is, we want to find a point in the D round closure. And then, so the Chvátal rank lower bounds depth. And so, this would imply a depth lower bound for cutting planes. So this was the strategy that was used in this paper by Burish Oppenheim and a bunch of other authors. So they wanted to find a point that's in the D round closure of this polytope. And to do this, they showed that they gave a condition for a point to be in the D round closure. They showed that a point P is in this closure if for every fractional coordinate in this point, if you fix it to either 0, if you fix it to both 0 and to 1, then this is in the D minus first round of the closure. So you get a little picture like this. So basically you can characterize, you get a necessary condition for the points that are in the D round closure if in terms of points that are in earlier closures. So this is gives you a nice way of looking at these things. However, their proof crucially relies on analyzing these CG cuts, specifically it's very syntactic in that sense. And there's not really an obvious way in order to account for proof size when looking at Chvátal rank. So if we wanted to do this size depth trade-off stuff that I was mentioning, then this doesn't seem like the nicest way to do it. Even so, our proof takes a lot of inspiration from this approach. And so kind of the result that we get is that we show that DPLL depth can be lifted to semantic cutting planes depth. And what do I mean by lifted? I mean that you take a formula F and you lift it by composing it with a gadget to get some other formula. So in this case, we're composing with a 4-bit XOR. So we take F, we replace each variable with the XOR of 4 new variables. So there's all the new variables. We have one block, so a block of new variables for each initial variable Zi. And then our theorem says that for any CNF formula, the depth of refuting it in semantic cutting planes, when you compose it with this XOR, is at least the DPLL depth over 2. And then we get the Tseitin lower bound. So the Tseitin lower bound isn't proved by using this lifting theorem, but basically all the nice ideas that we use for proving the depth lower bound on Tseitin are used in order to prove the lifting theorem. The lifting theorem is nicer to state. But basically, once we have this lifting theorem, we do kind of the standard thing and we replace lifting with expansion. So you can kind of think of as lifting as injecting expansion into the formula. And so if you just have an expanding formula, you can often just replace lift with just expansion. Yeah, so that's the last result in our paper. So I'm not sure how people are feeling. I can go into some details on this proof. I can go into a lot of details on this proof. I think there's some nice ideas into it. In it, but perhaps it's the least surprising result in our paper.
I would be interested in hearing, at least the nice details. Sounds nice.
Yeah, sure. Yeah, okay. So I don't know if you're familiar with like depth lifting theorems, like how to lift sort of like, I guess, tree-like resolution depth to tree-like resolution size, or proof is like has similar ideas to that, or like any sort of other like depth lifting theorem. Yeah, so the goal in our proof is we fix the semantic cutting planes refutation of this lifted formula, and we just want to find a long path in this proof. And as usual, we're gonna, there's a long path. We're gonna say that a half space is good if it is falsified by the all a half point. So this is sort of technical for right now, but like this is kind of an idea that we used from this Burrish-Oppenheim paper. So you should think of that as kind of analogous to their criterion. And how our depth lifting theorem is going to work is we're going to start at the root, and we're just going to walk down the proof. And this is standard. And we're going to be guided by this DPLL proof, right? So the DPLL proof has to be deep, and we're going to use the fact that this DPLL proof is deep in order to guide our walk. And to do this, we're going to maintain a restriction, like a partial restriction to the variables. And we're going to keep updating it, and it's going to tell us which way to go at each step in the proof. Okay. And the restriction is going to satisfy the following, so that if our current half space H under the restriction rho is good, that means it's falsified by the all half point. Then first, H is not a leaf. And second, we can find another restriction rho prime such that one of the children, H1 or H2 of H, is good under rho prime. And rho prime is going to be obtained by rho by setting 2 additional bits. And this is why we get this like divide by 2 in terms of the depth. And the main technical lemma behind our proof is it's this nice geometric lemma, which says that if we have H and we have 2 children of it, and H is good under this restriction rho, then as I said, you can obtain rho prime by fixing 2 additional bits, such that one of the 2 children is good under rho prime. So basically, this is saying like H is falsified by the all a half point. Then maybe H1 and H2 are both not falsified by the all a half point. But if we take this all 1/2 point and we fix 2 of its bits, there's a way to fix 2 of its bits to 0, 1 values, such that under this fixing, then under this restriction, then one of the 2 children is falsified by this all a half point. And this is going to let us continue. Okay, so assuming the technical lemma, I'll show you how to prove this thing. Proof still has some nice ideas. So there's the theorem. So we're going to denote D to be the DPLL depth. And we're going to maintain the following invariants. So you should think of as being at some half space in the proof, and we're just walking down the proof, and we're at a half space, and we've maintained some restriction. So initially, the restriction doesn't set any variables, and the half space is 0 greater than or equal to 1. Clearly, the all half point falsifies 0 greater than equal to 1. And the invariance we're going to maintain is that H restricted by rho is good. This consistency restriction, which is that if we take our our restriction rho and we apply this 4-bit XOR to it, so we're just projecting rho down onto the variables of just F, like the variables over which DPLL operates, or the variables where F is defined on, then this projection doesn't falsify F. So all this is saying is just like our current restriction doesn't falsify any of the axioms. So this means that H is not a leaf of the proof. And finally, this block closed notion, which says that rho sets all or none of the variables in every block, right? So remember that a block, it's behind, yeah, so a block, like the variables are broken up into blocks according to the initial variables. Yeah, so those are the 3 things that we're going to maintain. So this is just the previous paragraph from the last slide. Okay, and now we're going to see how to walk from H to one of its children. So we're at H and we have a restriction rho. We apply the technical lemma. We get a child, let's say it's H1 of H, and a restriction rho prime, which sets 2 additional bits. And now we want to restore the invariance. And basically the thing we need to restore is this block closedness thing. And we need to set it in such a way, we need to set the remaining variables in the blocks that have not all variables, right? So by the technical lemma, rho prime sets 2 additional bits. So there's some block, there could now be some block where not all of its variables are free or fixed. And so we have to set the remaining variables in that block. And we want to do it in such a way that we don't falsify any constraint of F. Yeah, so we're going to set the remaining variables. And what allows us to do this is this following claim. And I'll show you to prove it's very simple, but it uses properties of half spaces, in particular that they're monotone. So this claim says that if a half space is good, then for any subset of coordinates and any assignment B in 0, 1, there's an assignment pi to the variables that are indexed in the set I, such that the parity of the variables that are set by pi is B, and this half space H under this restriction pi is good. So all this is basically saying is that we can take, we have these blocks where one variable is, or 1 or 2 variables are set in them, but not all 4 of the variables are set. And we want to set the remaining variables. And this claim is just saying there's a way to set this, there's a way to set these variables such that H remains good, and the parity of the block of the variables in this block are whatever we want it to be. It can either be 1 or 0. We're free to choose it. And yeah, so that's what we do. So let I be the index of some block, which is not closed. So that means some variables are set, some variables are free. And we're going to set the remaining variables. So there's the blocks again. So first, we're going to query the DPLL strategy. I'll say what this means on this assignment, on the projection of rho prime for some value B, which we should set the ith variable of F to be consistent with a length D path. So what do I mean by all this? So we have a DPLL proof, and we know that any DPLL proof of F has to have depth at least D. So it has to be really long. And we're going to use this in order to figure out how we should set this block, the ith block, in order to be consistent with a really long path. So we've been consistent. So like up to this point, we're going to keep doing that. So we take our current restriction rho prime, and we project it down to the variables of f by using XOR. And this gives us a path through the DPLL proof. It's a path that is consistent, like it's a deep path. And we just need to figure out what the next step we should take in this deep path is. So we ask, like, we look at the DPLL proof, and we say, okay, should I set Zi to be 0 or Zi to be 1? There has to be one of these two settings, which is consistent with this really long, deep path. And so this gives us a value b to set Zi to be, which means that this gives us a value b to set the parity of the block I to be. And then we just apply the claim to the variables in block I to get a restriction pi, which is consistent, which sets block I to be the parity of block I to be b, and such that H is still good. So H under this restriction is still falsified by the half assignment. Okay, so that's basically what you do in the proof of the depth lower bound. The only things I haven't told you what to do are this claim and this technical lemma. So yeah, maybe there's a good time to ask if there's any questions or if there's anything I should be more clear on.
No, so can you say for which gadgets this is going to work?
Yeah, so this works for a 4-bit XOR. Maybe it can be made to work for a 3-bit XOR. You're definitely using some nice properties of parity here, like in particular in this claim. Yeah, I mean, I think it should basically work for any like non-trivial gadget. Like the properties of the gadget you need are not very strong. Like you basically need everything that's said in this claim. So you need to be able to set a subset of coordinates so that it gives you the output that you want. But that's really it. So like it should definitely work for like index or something like that. But 4-bit XOR seemed like the natural, the weakest one that we could get to work for. Yeah. So maybe I'll show you how to prove this claim because it basically shows the properties of this gadget you need. Oh yeah, so we should check the invariants are satisfied. So we're going to let rho be, our restriction that we've constructed so far. So it's going to be rho prime together with this pi, and H to be the child H1 that we've gone to. And we just need to check that each of these things are satisfied. So H restricted by rho is good. This is by definition of the claim. The claim just said, we can set things so that it remains good. Now we want to say that H1 is not a leaf, which means that the projection of the XOR projection of rho doesn't falsify any constraint of F. And this is because we've set things according to this DPLL strategy. So we've just used DPLL to find a long path in the proof. We've been consistent with DPLL, so this can't be a leaf unless our depth is like D. And finally, this block closedness thing, which says that every block has all of its variables free or set. Yeah, this is by construction, this is satisfied. We can proceed to the next round. And at each round, we've set at most 2 blocks of variables. And that means that we can proceed for the depth of decision tree over too many rounds. Yeah, and this proves the theorem. So the claim here was that for any half space and any subset of the coordinates and any bit b, we can find an assignment to the variables in this subset I such that the parity of the variables is B, and the half space remains good under this assignment. And this proof's pretty simple. The main tool here is monotonicity of half spaces and the fact that H is falsified by the all a half point. So yeah, we're going to denote H by this linear inequality. And let's say that I is the first K coordinates. And also we're going to order we're going to suppose that the variables, like the weights of the variables are ordered so that the largest one's on the leftmost side. Okay, and here's an example. And we're going to say that, you know, the subset of coordinates is 1, 2, 3. And basically all you got to do here is you just set the first k-1 coordinates in the direction you want them to be set to compensate for having to set the last coordinate to give you the parity output that you want. Yeah, so for the first k-1 coordinates, you set them to be, so you want to falsify the all a half point after this setting. So I'm going to set them so that the value of the half space is as low as possible. So if AI is greater than or equal to 0, then I set the variable to be 0, and if AI, and otherwise I'll set it to be 1. So this decreases the value of the half space. It'll make it easier to falsify. So here in my example, I've set the first one to be 0, the second one to be 1. And then for the last bit, I just set it to be equal to the parity, like that. And x4 is never going to be set. And then we just want to verify that this is true. So yeah, we're setting the first k-1 coordinates to compensate for having to set the last one in some direction. And we want to show that the half space is good under this assignment. So I'm going to do it for this example. So if we plug in the all a half point, so we fix the first 3 bits, and then the last bit is the only one that's free. So here's the assignment, and then this is less than or equal to setting each of these bits to a half. And this is just because like we set each of the bits to be the lowest value they could be. So if you set them to be a half, this will increase the value. And then this is less than the range. That's the whole idea of the proof. It's pretty simple. So the main juice of the whole proof is this technical lemma. This has got some nice geometric properties. I'm not sure if you guys want to hear about it. It's up to you. If you're feeling a bit worn out, you can skip it. But yeah, so the technical lemma says that if H has 2 children and H is good, then there's a way to fix 2 bits of, fix 2 additional bits so that one of the 2 children is good. This allows us to continue to one of the 2 children. Yeah, so how are people feeling?
Well, go for it.
Okay. Yeah, so I'm going to give, I won't do all of the details of it, but I'll give you a high level, again, idea of what goes into it. So we're going to do a change of basis first. It's easier to work in the +-1 basis rather than the 0, 1 basis. I mean, it's only slightly easier, but like the nice thing that we're going to use is that the all a half point becomes the all 0 point, and there's a bijection between the 2, so it's okay. Yeah, so again, H is good now if the all 0 point falsifies it. Okay, and we're going to assume that rho, like the restriction I've stated in the lemma, is just the all star restriction. It's yeah, doesn't change anything in the proof. So here's the half space. The stuff colored in green is the stuff that falsifies the half space. So In particular, we know that the all zero point is falsified by it. And one of the crucial things we're going to use is that, so the all zero point falsifies the half space. So the half space, if you look at it in this square, like the half space is kind of in the, like has to be at least kind of in the center. Like there's always going to be a corner of this square that the half space falsifies. Like falsifying the all zero point like positions the half space in a nice location for us. Yeah, okay, so one thing we're going to use is, soundness means that every point which falsifies H is going to falsify every integer point. Integer now means over plus minus 1, which falsifies H is going to falsify one of the two children. But this doesn't mean that fractional points, so 0 is considered a fractional point in this world. This doesn't tell us anything about these points. So while 0 may falsify H, it doesn't have to falsify one of the two children. So here's a little picture, it lies outside of H1 and H2, blue in the red areas are the areas of points that are falsified by it. We're going to denote the half spaces by A1, X squaring the B1, A2, X squaring the B1 or B2. The first step, so basically the high level idea of what we want to do is we want to start at the all zero point and walk in some direction so that we land, so that we fix only 2 coordinates. So we're going to only walk in like 2 coordinate directions from this 0 point so that we land within the falsifying area of H1 or H2. So yeah, so I won't show you how to get this vector, but it's not that hard. But we're going to find some vector which lies in -1, 1, which is orthogonal to A1 and A2. Like it's orthogonal to the vectors defining these 2 half spaces, such that at most 2 coordinates of this vector are not -1, 1 valued, or not Boolean valued. And these at most 2 coordinates are going to define directions for us to walk in order to like land within one of the children half spaces. Okay, so in particular, the thing we're going to use is that because V is orthogonal to both H1 and H2, walking in the direction of V doesn't affect the value that V has, that the point has on H1 and H2. So, A1 of X plus V is equal to A1 of X. And we're going to let C be the corner, like the Boolean valued point, which is closest to V. And that's the point we're going to kind of walk toward. Okay, so yeah, okay, so yeah, so V either is falsified by the half space H or is not. And we can assume that it is falsified by it, because otherwise we can just set V to be -V and C to be -C, and we still have all the nice properties we want of V. Like V is still orthogonal to both the things. So we can assume that V is falsified by the thing. Now, because
sorry, just a minor point. When you write H of V equals to 0, you mean less equal?
Yeah, sorry. So I'm writing H as like a function.
Okay.
Yeah. This should be, instead of V, this should be C in these last 2. So because C is Boolean valued, either like C is Boolean valued and C falsifies H because V falsifies H, then C, like the Boolean value point, has to falsify one of H1 or H2. So we know that C is also in the falsified region of H, but this also means that C is in the falsified region of H1 or H2. So let's suppose that it's H1. So now we have a picture that looks like this.
And just to, so I think, yeah, it's getting late in the day, but this is just to, you're saying that the magic here is that you only need to walk 2 steps, but this here, we're not using any properties of these 4-wise XOR substitution or anything, or this is
no.
This is a general claim about hyperplanes.
Yeah, exactly. The only properties here we're using is that hyperplanes are monotone in nice way.
Okay, and then the fact that the 4, I mean that so you need to pick at least 2 variables here potentially. So that tells you that the XORification has to be at least an arity of 2, and then I guess you pick up a factor of 2 on top of that somewhere, which I don't currently see, but.
Yeah. So you need at least.
I guess the 4 is like this. The 4 comes from this 2 plus some margin from elsewhere.
Yeah, exactly. Yeah, 1 bit is obvious because you need. You need 2 from this guy. You need one additional bit for setting the parity, and then there's another slack one that you need. But yeah, this technical lemma here is only relies on properties of the half space. So we were hopeful that maybe this could be used more generally. Like this actually came out of an attempt to prove lower bounds on the Tseitin formulas for cutting planes. So yeah, that's where all these tools come from. So we're hoping that maybe it can be used more generally. So this is just saying if you can fix at most 2 coordinates to have the all half point falsified by one of the children. And also something that maybe I should note is that it's not sufficient to set only 1 point. Like there's a counterexample against that claim for 1 point, which is different. If you compare this to the Burish-Oppenheim thing, they are allowed to set only 1 point. So just finish this up. Basically, we're going to use V and C, which are orthogonal to A1 and A2 in order to walk to the point that we want. Okay, so again, let's see if I can just write here. You should be C. So we know that C is falsified by both his children. We assume that it's falsified by at least one of them, and we assumed it's falsified by H1. So then we're going to just start at the all 0 point, and we're going to walk until we hit a side of this square that we're on. And we're going to walk in the direction of C minus V. So C minus V, so C is the closest corner, the closest Boolean point to V. So that means that C minus V has only 2 non-zero coordinates. It's the fractional points, corresponds to the fractional points of V. So we walk in this direction until we hit the side of this square, until one of the coordinates of C minus V becomes -1, 1 valued. So we're going to let alpha be this point. So we started at 0, we walked in the direction of C minus V, and we walked for some alpha steps. So alpha is some rational until we hit this side. So alpha C minus V is the minimum alpha such that C minus V has only one non-zero, one non-1, 1 point. It should be one non-1, 0, 1 point. Okay. And so we can assume that alpha is greater than 1 because C is the closest corner to V. So their infinity norm is the most 1. And so now we just want to verify. Now we're going to verify that this alpha times c minus v is also falsified by h1. So alpha times c minus v is basically going to be our restriction. So if you look at if you look at c minus v, then there's at most 2 non-zero coordinates. And alpha times c minus v fixes one of these 2 coordinates to plus minus 1. And we're just going to fix the last one to plus minus 1 in a second, but we want to verify that this point is already still falsified by h1. So expanding it out, you get this. Now, because v and a1 are orthogonal, you get, just the alpha a1 c, and this is because the infinity norm is m-1, this is m-b. And then the very last step, so we verified that alpha of c minus v is falsified by h, has 1 coordinate which is not in 0, 1, plus minus 1. And what we're going to do is we're just going to take that last coordinate and we're going to round it. And one of the 2 directions by the monotonicity of h, one of the 2 directions that we rounded in either to 1 or minus 1 or plus 1 is going to be still falsified by h1. Right, and this is just because h1 is monotone, and also because, So you take the last coordinate and you just round it to one of the 2 sides, and one of the 2 sides is going to be falsified by h1. And there's a little drawing of moving there. So now we found a point P, which is P star, which is in -1, 0, 1, such that at most 2 coordinates are in -1, 1. And it's falsified by h1. And this just defines our restriction. We look at the 2 coordinates, which are in -1, 1. That's our restriction. And under this restriction, the all 0 point falsifies the half space. And so the half space is good. And that's the, maybe I shouldn't say high level, but that's the general idea of what is going on in this lemma. You're starting at, you're starting at the all 0 point, which may not have falsified one of the 2 children, and you're just walking in some directions in order to set 2 of these coordinates to plus minus 1 value, such that you falsify one of the 2 children.
So is it correct? Somehow it's a bit counterintuitive, but you said that you have to have 2 coordinates non-Boolean to find this point that is falsified.
Yeah, so it's okay if less than 2 coordinates are non-Boolean.
Yeah, but you can't guarantee that. So that you might have 2.
Mm-hmm.
And then, okay, so now I need to round to do something Boolean. And then I pick is the intuition. Then I pick the guy with the largest coefficient and round that in the right direction somehow. And then the other guy, even if it gets rounded in the opposite direction, it won't mess things up for me, or no?
No, so we're not using that here. What we're doing is we're just we're just taking this walk until we hit the side of the Boolean cube, and this sets one of the coordinates to -1, 1 value, because we're just walking in the direction of that coordinate.
And remind me again, how did we find which wall do we want to hit? Do we know?
So it's defined by this vector v that I haven't told you how to get. Basically, the properties of v, though, are that they're orthogonal to a1 and a2, like the coefficient vector of h. And so this means that walking in that direction doesn't change the value that h gives to this point. besides this alpha. Yeah, and so we just use this and we walk in the direction of that vector minus the corner that's closest to that vector. So why are we subtracting off this corner? Well, because if you subtract off this corner, then every coordinate becomes 0 besides these two like fractional coordinates.
But somehow the corner that is closest will correspond to the one of these two variables with the larger coefficient, or no?
Yeah, good question. I think it should correspond to the one with the higher coefficient.
That somehow, my intuition is that you'd pick the highest coefficient and you set that guy right.
Mm-hmm.
And then no, but yeah, okay. No, I don't know. I fooled myself into somehow believing kind of sort of, I shouldn't ask too much because I still have hope that I understood what you said. So let's leave it.
Yeah, I mean, I think that is right. I think you are rounding the one with the highest coefficient in this C minus V vector, basically. And then the last coordinate can just be rounded by using the monotonicity of H. It's just like once you have a vector with once you have a vector where all coordinates are either in 0, 1, -1, besides one of them, you can just round that coordinate in some direction, either to 1 or to -1, because it lies between 1 and -1. It's falsified by H, so that it just, it makes H more falsified.
Yeah. Mm-hmm. Yeah. Mm-hmm.
Yeah, the picture is pretty simple. If you have like, this is your point here, and maybe this is the plus direction, this is -1, +1,
Mm-hmm.
then there's always going to be, and it lies in the Boolean cube, then there's always going to be a direction like this that you can send it in order to just decrease the value of H.
Mm-hmm. Yeah.
But yeah, that's the high level idea of what goes on in the technical lemma. And actually finding this orthogonal vector V is somewhat non-trivial. It's another kind of walking around the cube procedure. Yeah, so I guess I can end with some open problems, unless anybody has any questions before that. Yeah, so natural open problems are, I think the most interesting ones are like the ones that come out of this simulation of low weight stabbing planes by cutting planes. Like, can we improve this? Is this optimal? Yeah, I really don't have any intuition either way. Like, in some sense, like our simulation of low weight stabbing planes by this face-like stabbing planes it's just doing the dumbest thing possible. Like we're just like taking all the possible slabs going from left to right, and then we're just pasting the subproofs on each leaf of this thing. Like there's tons of redundancy. Like just say a couple of words. I'll try to go back. To this. Yeah, so there was our picture. There's our proof. Like you're just taking the left subproof, this pi L, and you're pasting it on each child, like on each leaf of this proof. So there's tons and tons of redundancy here. Like the proof pi L prime, like the left subproof, is refuting something that's way more than what it has to refute. It just has to refute one of these red lines, but instead it's refuting all of this like pink area at each leaf. So maybe there's some way to like make this more efficient. Yeah, I mean, I've thought about it, and I think it's a really interesting question. And yeah, so this also brings up a lot of questions about the relationship between cutting planes and stabbing plane star. Can cutting planes just simulate it? As I said, can cutting planes quasi-polynomially simulate stabbing planes? Can cutting plane stars, so this is bounded weight cutting planes, like with quasi-polynomial coefficients, can that simulate stabbing plane stars? So the annoying thing about this Shriver lemma is that when we apply it, when we shift the half space that we had, this can blow up the coefficients significantly, and it can, yeah, it would be really nice if we could like maintain the size of the coefficients. Like it'd be nice if we could say that like up to a quasi-polynomial difference, cutting plane star is equal to stabbing plane star. And this is of course related to a lot of questions in related like around cutting planes as to the like power of like the power of coefficients in cutting planes, which I know you've done some really nice work on. Both Jakob and Susanna and Mark, I believe. Yeah, and then there's also like a DAG-like version of stabbing planes. It's this RCP proof system introduced by Krychek. Can we like understand better the relationship between stabbing planes, cutting planes, and this DAG-like stabbing planes? So we know that cutting planes can't simulate it because it has short proofs of the clique coloring principle, but for very large cliques and very small colorings. So this only rules out like polynomial simulations. There could be a quasi-polynomial simulation. I think it would also be interesting in the other direction to show that so this proof of that RCP or this DAG-like stabbing planes can do clique coloring is it's actually proved for res k. So you'd think that like DAG-like stabbing planes or this RCP, which is resolution over cutting planes, so the lines can be disjunctions of linear inequalities. You'd think this would be like significantly more powerful than res k, which operates over DNFs. So can we improve the simulation? Can we improve the upper bound for the clique coloring formulas in res k? I think that would be nice, and then show an actual separation between that and cutting planes rather than just like a polynomial separation or quasi-polynomial. Yeah, and another nice problem I think is to try to refute systems of linear equations in tree-like cutting planes. Yeah, again, this one seems tricky because we don't have. So it's the same problem that we have with cutting planes. Like cutting planes, all lower bounds are by reduction to communication complexity or reduction to monotone circuits, same thing. And it's the same for tree-like cutting planes, except for you're reduced to like randomized communication or real communication rather than these like DAG-like communication models. So I think a really great problem would be to try to like, it's maybe kind of obvious, but like try to get combinatorial lower bounds for tree-like cutting planes first. Like everybody talks about trying to get them for like cutting planes, but they're not even known for tree-like cutting planes. Yeah, I think that would be really neat. Can you even get like a, I guess the like BPP lifting theorem would give like a lifting theorem for tree-like cutting planes perhaps, but yeah, so that's my talk. Thanks for sticking with me. Yeah, does anybody have any questions?
Thanks a lot, Noah. Let me just add the round of applause on behalf of everybody first, and then we'll certainly let people in for questions. Thanks a lot for a wonderful talk again. Questions from the audience?
No? Do you hear me?
Very lightly.
Okay. I'll come closer. I don't know what's going on there.
I can turn up my volume.
Hmm?
Yep, that's good.
Okay. I had a couple of questions actually. First of all, when you mention, like you show the technical lemma and you have to fix two variables, two non-integer coordinates,
Mhm.
basically because you have two inequalities in the row, right? You have these, right?
So no, I don't think that's the reason you have to fix. Well, you have to fix at least one point because if I go all the way back, right, because all 0 point might not lie in one of the two half spaces. But for, you can see this lower bound technique is sort of like if you blur your eyes, like a semantic generalization of this Oppenheim et al. Like Chvátal rank lower bound. And there it's actually enough to just fix a single coordinate. So the two, I don't really have a good reason for why the two is necessary rather than just one, besides that there is like a pretty simple counterexample against fixing just one. But yeah, so I don't think it has to do with the number of children.
Because you say that you have like you find the V orthogonal to A1 and A2, such that almost two coordinates V are not plus or minus one. But so it doesn't matter if you have like three inequalities or four inequalities, and so you have A1, A2, A3, A4. That doesn't matter. I mean, it doesn't influence the fact that you.
Yeah, that's a good question. I'm not quite sure. I think it wouldn't matter. Because it has more to do with the dimension. But yeah, I'm not sure. I can look at that. That's
I mean, the way it's written, I thought that was somehow what was one of the reasons.
Yeah.
So it means that it wouldn't this result it may not degrade if you want to consider like semantic cutting planes with three premises or four premises. It would be still like maybe depth of DPLL divided by, I mean, the XOR would be still like a 4-bit XOR. It wouldn't be like 5 or 6.
Yeah, no, I think it should stay the same. That would be my guess, but yeah.
Thank you.
Yeah.
Oh, by the way, just no pressure, but are you going to put your slides somewhere?
Oh yeah, definitely.
Okay.
Yeah. I'll Jakob, are you hosting the slides?
We totally could. I've been a little bit lazy in putting up slides, but I've been thinking about collecting slides from the speakers and put on the webpage. Now that we're linking to the videos now, and I think it would be nice. Yeah, I mean, I'd be super happy to host slides. It might be a natural thing to do.
Yeah. I'll also
I agree. These are like fantastic. I mean, it would be great to have them. Yeah.
It took. Yeah, I mean, there's like 300 slides, so kind of went wild with them.
Yeah, I mean, you mentioned this about this starred versus non-starred version to separate somehow that, to say if you only have small coefficients that it makes a difference. It's interesting. I mean, we did manage to get a setting where, as you mentioned, we have like one setting where you can prove that smallness of coefficients really hurts you, but it's like it's somehow a very specific setting, this size space trade-off. And it would be interesting to see if it could somehow be, because it seems to me like it's actually, I mean, what's happening here is in fact the kind of thing where like basically what we prove is that we find a very particular setting where if you have unlimited size of coefficients, then you can like pack a lot of equalities into just a single linear inequality by just spacing them apart. And this is sort of what you're doing here in this. I mean, this is Shriver's lemma, which I guess we should have cited, except that we didn't know about it. Because we're sort of doing the same thing. Like if you have a bunch of faces, a bunch of equalities, then that's just two linear inequalities, right? I mean, AX greater equal B and AX less equal B. And now if you have a ton of these, then you can just write them all in one by just spacing them apart so that they can't interfere.
Yeah, I see.
And that's what we do. And then we have a particular formulas where this, like packing several inequalities into one spaced apart, is like a very useful thing to be able to do. But of course, as you like pack more and more inequalities into the same inequality, obviously you need to go exponentially large, because otherwise the packing breaks.
Yeah, I see.
But it's a very, very particular setting in which we're able to prove a lower bound. I don't know if, or maybe Susanna has some thoughts for what we should do.
No. But do you manage to pack inequalities or equations?
Sorry, Massimo, I didn't hear you.
Do you manage to pack inequalities or actual equations?
So you have several equations you want to pack together. So you pack them all using two inequalities.
Okay. No, it's fine. No, I thought that you were, I understood that you were able to pack inequalities, which sounded like strange.
No, I have a question. When you were talking about face-like and path-like, what was the other name? Stabbing planes. Is there a communication model for these that is a tree-like kind of communication model? Because this is equivalent to cutting planes, so would you have some kind of tree-like version of it?
Yeah, that's a good question. I haven't really thought about it. So one thing that, I don't know, that's a good question. Like for path like stabbing planes, although the proof is like one long path, what you're actually doing is you're just repeatedly querying each of the CG cuts. And so it's like, it's DAG-like in like disguise a little bit, because each CG cut like depends on like each, you have a polytope and then you get a CG cut from that polytope, and then you get another polytope with that CG cut, and then you take another CG cut and whatever. And so it's stabbing planes, each line is a polytope. So that's why we're able to do this. But like each CG cut that you introduce along the way could depend on the previous CG cut and could become sort of DAG-like in, I don't know if this is making any sense, but yeah, what I'm trying to say is that when you look at the linear inequalities, like how you're inferring each linear inequality from the previous linear inequalities of this polytope, it could be DAG-like. But in stabbing planes, you basically are allowed to remember a polytope instead of like just a linear inequality. And so, yeah, that's why I'm not sure if there would be like a tree-like communication model for it, at least one where you're like, remembering half spaces at every leaf. I mean, at every node. You could maybe do something where you remember polytopes, but then I feel like I would just be redefining stabbing planes in the communication world. Yeah, it's a good question though. I think like if you could get like any sort of communication model for like a nice communication model for like stabbing planes, I think that's also like a really good question. Yeah, I definitely thought about that. And there's yeah, there's nothing really nice. Like basically the problem is that at every line, like in stabbing planes, you take a polytope, you stab into it, you bisect it into two subpolytopes. And these inferences are not sound in the way that proofs usually are. Like they are sound, but like usually in proofs, you have two lines, you take a sound deduction from them. In stabbing planes, you're not like taking two lines or previous lines and deducing a new one. You're doing this like splitting thing. And this like different type of soundness like is problematic when you try to make communication models, I find at least. Yeah. I was wondering something about what you and Jakob were saying. So space is related to depth, right? At least in resolution. So I was wondering if this could be somehow related to be used to tackle this conjecture, like your well, yeah. So I was wondering when you were saying that if you could use your result somehow in order to show that this reduction from stabbing plane star to cutting planes is optimal, or this like this need for coefficients is optimal. So right, so sorry, I'm not being very articulate, but like there's two dimensions to this reduction that I'm interested in reducing from stabbing plane star to cutting planes. One is, size. I'd like to get smaller size proofs. The other is depth. I'd like to make this translation not blow up the depth like into the size of the proof. Like basically now you turn a size S proof into a depth S, size S cutting planes proof. So for resolution, at least, clause size is equal to, or is related to depth. So I was wondering if there was some way you could use those. I'm not, yeah. So is your result proved for cutting planes or for tree-like cutting planes? And if it's for cutting planes, are you using the like Gargadal lifting theorem, or, I mean, not tree-like cutting planes, just regular cutting planes?
So you're asking about the results that separates this in size space separation between bounded coefficients and unbounded coefficients, right?
Yeah.
Okay, that uses the Tassi-Robert lifting theorem, because since you're in this size space world, you only need a tree-like type of lifting theorem.
I see.
So the one that lifts no stolen sets.
I see.
Yeah, and something annoying is that we don't know how to have simulation style version of that lifting theorem. So it's a one-shot kind of thing. It's algebraic. So since we don't know how to make it simulation, we don't know how to make it DAG-like. That's
I see. By simulation style, you mean like reducing to like resolution or something like that? Like,
yeah, this very nice, let's simulate the decision tree kind of thing.
Yeah.
Step by step.
That's a very good point, right? I mean, I think we should maybe return to it at some point. I guess we're out of energy, but the lifting theorem to me is like extremely mysterious, because it goes via like, goes to Nullstellensatz and then goes to these, what is it, like, I forget, non-monotone spanning programs, and like, it's like this immense detour, and then by the end of the route you say, oh, I arrived at my destination, but by what route? It's like, it's a mystery, but it's like every single step works, but it seems like, yeah, a direct simulation style argument would be so nice.
Yeah.
But it's really a chain of like piecing things together in a somewhat mysterious way.
Yeah, it's definitely mysterious as to why like each of those is the right step to take, at least for me.
Yeah, no, I don't think they are. I mean,
I remember I was there when Robert proved it, and the board was just like, just like I think he was working on like some sort of gen graph, and like he had equations for all of them. It's like one of those like moments in like a math movie where the person has like an insane amount of equations, and then he's like basically like yelling at the board, like, why are all these things canceling? Why is this working? So I'm sure he understands it better now, but I think when he originally proved it, it was like, yeah. Yeah, I wonder if that lifting theorem, if you could refute, like, you need like low rank gadgets, right? So I wonder if you could like prove lower bounds in the Tseitin formulas using that lifting theorem for tree-like cutting planes. Or like lifted Tseitin, like.
Yeah.
Maybe XOR has too low rank.
I don't know, it sounds plausible to me. I have to think about it.
Yeah, it's like definitely something somebody has thought about, because it's very obvious, but like.
No, but it might be the rank thing, right? Does XOR have only constant rank?
Yeah.
As in it's the kind of thing that you just, I mean, one of the players sends the XOR of half the variables to the other one,
Yeah,
right?
yeah, yeah. As rank 2, right?
Yeah.
Yeah. Yeah, that's probably the problem. You need like rank 3 or something. Like it's like a constant, but like slightly more, I think.
Right. Yeah. Large enough constant should work. I don't know if 2 is large enough.
Huh. Weird.
Okay. Other questions, comments? Before we let Noah off the hook.
Yeah, thanks a bunch for having me.
Yeah. Thank you so much. This was great.